Hello and welcome, Nord Anglia, and thank you for joining us today for our MIT abstract on A Star in a Jar with MIT graduate student Shon Mackie. I'm your host, Fatima Hussein, and I'm a PhD student at MIT studying ancient Earth. Now, before we begin, I'd like to cue you in to what an abstract actually is. An abstract is simply a snapshot or a summary of a greater work of research or writing. And what's really exciting about our series, MIT Abstracts, is you have the opportunity to ask our amazing speakers questions about their research. Now, for the really exciting part of our series, I get to introduce our amazing speaker today, Shon Mackie. He is a real star on Earth. Shon studies plasma fusion, the science behind the stars and the sun, and he's a graduate student in the MIT Department of Physics. Welcome, Shon.
Hello, I'm Shon, and I'm going to be talking to you guys about stars and jars and fusion energy. But first, I want to tell you a little bit about myself. Like Fatima said, I'm a plasma physicist in training. I study plasmas, which are the fourth state of matter, in order to learn how to harness the same sort of processes that power the sun to produce clean, sustainable energy. I've always loved math and science, and so I decided to study physics so I could help create technologies to help society overcome the challenges that we're facing. So global climate change, energy crisis, and pollution. These are all issues that I'm really interested in figuring out solutions to. Besides studying and doing math and science, I also like to canoe, I like to ski, rock climb, and I love to read. So, like I said, I'm studying plasma physics to figure out how to do fusion energy, and that's because I believe in a fusion-powered future. Fusion is the process that gives the stars their energy. It's basically the entire universe relies on fusion, and if we could figure out how to apply this process here on Earth to generate power, it would really change a lot of things for the better. So a little bit of background. The fuel for fusion is isotopes of hydrogen. So it's very abundant. You can extract it from seawater, or you can collect it from the solar wind in space. It's all over the place. It's the most abundant element in the universe. The energy generation from fusion is much more efficient than any other means of power production. There's about 8 million times more energy per gram of fusion fuel than there is in gasoline. And this doesn't produce any greenhouse gases. It doesn't produce any pollution. It has the potential to completely change virtually every industry for the better. And it'll enable totally new innovations. Before we get into the details of what fusion is, it's important to think about what is plasma. It's the fourth state of matter, but what does that mean? So if you think about matter, all matter is composed of atoms, which are these tiny fundamental building blocks that everything else is made of. Atoms are basically a positively charged nucleus surrounded by a negatively charged cloud of electrons. If you think about the way that atoms get arranged in matter, in a solid, all the atoms are closely packed together in a lattice, and they just sort of jiggle around. But if you add some heat to that solid, the jiggling motion gets bigger and bigger until eventually the atoms sort of break apart from each other, and they're allowed to fluidly flow around. That's called a liquid. If you continue to add heat to a liquid, the atoms continue to jiggle around until eventually they break free of that slight fluid bond holding them together and you get a gas. So boiling water gets you a gas. If you continue to heat a gas, the thermal motion of these atoms becomes so great that when they bump into each other, they can actually blow the electrons away from the nucleus, and you end up with this ionized gas called a plasma. And plasmas are a distinct form of matter from gases. They have some similarities and they have some important differences. And one of the most important differences is that they respond to magnets and they respond to electric fields. So plasma, you probably don't think that you've seen one, but plasma is everywhere and you have definitely seen one. If you've ever gotten a shock when you touch a doorknob from static charge, that's a plasma. For a brief instant, that little arc is a plasma. Neon signs are plasmas, lightning is plasma, the sun, the stars, these are all plasmas. And if you look into space, it's the most abundant form of matter. 99% of the matter that we can see in space is plasma. So this is, if you ever hear someone talk about space dust, that's actually a plasma. If you look at pictures of nebulas or galaxies, it's a lot of plasma that you're looking at. So how do the stars produce their energy? This is going to be a little bit of complicated physics, but bear with me. The basic idea is that inside the cores of stars, the plasma is so hot and dense that the positively charged nuclei, they want to repel, but if they have enough energy, and because they're so hot, they can actually slam together and fuse. And so this fusion reaction produces a lot of energy. So much energy that all of the heat that we feel, all of the light that we see from the sun, that's all just a result of this fusion energy being radiated away. When you look into the night sky and you see all the stars, you're seeing the light of millions of fusion reactors going off. And this stellar fusion process is also how all heavy elements are created. So everything heavier than hydrogen is made inside these fusion reactions inside of stars. And so in a sense, everything around us is a result of these fusion reactions. So we understand pretty well how stars make their fusion work, and it's because they're so big that they're able to compress the plasma so much. Scientists and engineers have been trying to figure out how to recreate these conditions here on Earth for the past 70 years. And it's a really difficult challenge because, one, how do you heat something up to be as hot or hotter than the core of the sun? And two, how do you actually contain something that hot? I mean, any box that you try to put that plasma in would instantly melt if it came into contact with that material. And so there's a number of different approaches, and we're making steady progress towards making fusion energy a reality. Progress is happening now. There was a breakthrough in December. The National Ignition Facility in California demonstrated a very brief net energy fusion reaction in this big chamber. It's called the NIF. They basically shoot a bunch of lasers at a tiny pellet of fuel, compressing it, heating it, and then it blows apart, and a very brief but very energetic fusion reaction occurs. So in this experiment, they actually got 1.5 times more energy out than they put into the reaction. So that's a huge breakthrough. But it's not necessarily directly applicable to generating energy for society. So if we want to do that, we need to think about how can we sustain this reaction? And the way that we can do that is we can use powerful magnets to hold the plasma in place as we heat it up. And the magnets keep it away from the edge of the vessel. And so the leading design for a fusion reactor is called a tokamak. And this picture on the left is a picture of the Spark tokamak that's under construction with a collaboration with MIT and Commonwealth Fusion Systems. So these tokamaks are basically magnetic bottles that hold the plasma tightly in place as we apply a bunch of heating, and eventually fusion reactions occur. Spark is supposed to be complete in 2026, and it's supposed to have a net energy plasma by the end of the same year. And so stay tuned on that. Hopefully it works out. The work that I do is building a set of detectors to measure how much fusion is actually happening in Spark. And so basically just counting the number of reactions that happen to make sure that we're achieving the goals that we're setting out to and understanding how exactly this plasma is burning. If Spark successfully sustains a net energy reaction, then fusion power plants will follow soon after, opening the doors for a new era of clean, abundant energy. There's a lot of potential in fusion energy if it does work, and I think it will. It can be used for electricity generation. It can be used as an industrial heat source. It can be used to power desalination plants. The possibilities are really endless, and it's up to us to think of creative solutions and creative applications of this technology to improve the world and society for everyone. By the time you're my age, fusion may become a commonplace technology, and so you guys should really start thinking about how would you like to see fusion applied. Personally, I really hope that fusion allows humanity to begin to truly explore the solar system. I think that it opens so many doors, and it's really exciting to think about.
Thank you so much, Shon. I think this is a really good question. How do you want to see fusion used? I'm going to let Nord Anglia students take a moment to think of some ideas and throw them in the chat, and we can go over them. But in the meantime, maybe you could tell us a little more about how it might be used for space exploration. Why would that be an advantage versus what we're doing right now?
Sure. So the current generation of rocket technology uses chemical propulsion. So basically we burn chemicals and then that produces thrust. And like I was saying earlier, the energy density of the fusion fuel is so much more dense. And so when you're trying to do things in space, it's important to not bring unnecessary weight, because everything that you want to bring up, you need to launch up with a rocket. And so if you have a rocket that uses far less fuel, you don't need to send up as much weight, and it's easier to send up larger, more complicated rockets, basically. Also, in space, the sun is constantly ejecting the fuel that you need to do fusion. And so once you're there, you don't need to constantly ship fuel up. You can just collect it wherever you are.
Awesome. That is really cool. So we could go farther, potentially faster and have that fuel source right next to us. That is super, super cool. Okay, we have a couple of questions here regarding the application of how Nord-Anglia students want to see fusion used. The first one is, how can fusion be used for clean energy? And while you're answering that, can you tell us what clean energy means?
Sure. So clean energy is energy that doesn't produce a bunch of waste. So if you're thinking about how most of the modern world uses oil as their main energy source, oil and coal. And so when you burn oil and coal, one, you produce a bunch of greenhouse gases, which have the effect of basically insulating the earth so that as the sun heats it, that heat doesn't radiate back out into space. And so that's one source of pollution. But also when you burn these chemicals, you get a lot of toxic byproducts. So things that wouldn't be good for you to breathe in. So in a sense, oil and coal are really dirty fuels, dirty sources of energy. Clean energy is something that doesn't produce byproducts like that. So solar energy is a clean energy that we have now. Nuclear fission energy is almost a clean energy, but it produces these long-lived radioactive waste products. Hydroelectric energy is a clean energy. Fusion is a clean energy because, like I said, it doesn't produce any greenhouse gases. The byproduct is helium, so that's like not a bad thing to be producing. It's inert gas. And there is some radioactive products that are produced, but they're much shorter lived and they're in much smaller quantity than traditional nuclear power.
Awesome. No, I think that makes a lot of sense and is really exciting. I use a lot of helium for my own research, so I'm excited to see if maybe we can harness some of that helium in these reactions, because right now helium is pretty expensive to buy. Okay, we have some really, really fun questions in the chat. I want to start with a question from a Nord-Anglia student, and they're wondering, you said during your presentation, it's really hard to contain plasma in a box because it'll melt the box. So this Nord-Anglia student wants to know, why don't electric shocks, like when I'm trying to grab that doorknob, why don't they melt us?
That's a great question. So not all plasmas are the same temperature. There's cold plasmas and there's hot plasmas. And a fusion reactor needs to be extremely hot. That way, the plasma will actually start to fuse. And that requires a lot of energy. The doorknob plasma is basically the same temperature as the air around you. It's just ionized, and so it becomes a plasma. Yeah.
That is definitely comforting. Okay, so we have another question from a Nord-Anglia student named Gulmahek. And Gulmahek is wondering, what is the proof that plasma might have existed before the Big Bang? And did plasma exist before the Big Bang? What do you think?
It's an interesting question, and there are competing theories about what the universe was like before the Big Bang. I am not a specialist in cosmology, so I can't say for certain, but if there was something before the Big Bang, it's likely that it was a plasma, because before the Big Bang, everything was so hot and dense, it can't have really been anything else.
Okay, got it. Yeah, lots to think about there. We have a few Nord-Anglia students who, might be a little concerned for your safety here. Okay, so they want to know, is your work dangerous, Shon?
Not extremely dangerous. I mean, I work with high voltages and high currents, so these are sort of electrical hazards. But as long as you know where they are in your lab space, you don't need to worry so much about them. And there is radiation hazard, but whenever I run an experiment, I'm behind like 3 or 4 feet of concrete, so I'm pretty safe.
That is super good to know. And you mentioned that your research involves creating the detectors that actually tell us how many reactions are occurring. Where do you put those detectors and how do they work?
So each fusion reaction produces a single neutron and a single helium atom. And so these neutrons aren't confined by the magnetic field and they stream straight out of the tokamak. And so the way my detectors work is basically behind the big wall around the tokamak, there's a little tube that neutrons can fly through. And at the end of my tube, I have a little camera that counts the neutrons that hit it. So far away from the plasma, just taking a little picture of it using the neutrons.
Okay. Oh, that is pretty cool. We have a Nord Anglia student now who's wondering, in all of this work, you showed us the pictures of you next to, a cutout of a tokamak. And they're wondering, what work goes into that? Do you work with other researchers? What does your team look like?
Yeah. So fusion research is extremely collaborative. These experiments are huge. So you saw that cutaway, and that's kind of modestly sized tokamak was that cutaway, and it's to scale. So these things are really big machines, and you need a lot of people to build them and then operate them. So just on the team that's developing these neutron diagnostics for Spark, there's like 6 or 7 of us working on it. On the whole Spark project, there's hundreds of people working on it. It's an extremely collaborative, it's a big group effort. It's not something that one person could build on their own.
Wow, I'm really happy to know that so much teamwork is going behind such an amazing project that has such potential to help, all of us and empower all of the things that we do in the future. I'm really excited for the students on this call, because perhaps in their lifetime, they'll be able to use this to power their computers and turn on and tune into MIT abstracts then too.
Yeah, it's great too, because everyone on the team has different skills, Not everyone needs to be a plasma physicist. We need electrical engineers, we need mechanical engineers. Everybody has a role to play. And every set of skills could be useful.
That is super true. So I want to take us back to some of the basic physics. Okay, so some of us on the call might not be as well versed in physics just yet, as you mentioned. So I wanted to go over, could you explain to us once again what plasma is and how you get electrons or electrons or atoms to move that fast in the first place to create it?
So if you want to understand a plasma, it's best to think back to what an atom is. And so you have this nucleus that's positively charged, surrounded by all these negative electrons. And these electrons are bound to the nucleus because opposite charges attract each other. And so they're bound together, but they're not bound super tightly. And so if you add a lot of heat, so these atoms are jumbling together really fast, then they can knock each other's electrons off, basically. You can also apply a strong electric field, and this will have the effect of ripping the electrons from the nuclei, and you generate this charged gas that way. There's a lot of ways to generate plasmas. There's probably more ways than I could think of right now. But it all sort of comes down to you have this bound atom, and you need to give it enough energy to unbind it.
It seems like, based off of those really beautiful photos you showed us of all that space dust, it seems like this state of matter is super, super common. We might not think about it every single day, but it's definitely all around us. We have a question from a student about some terminology here, and I think it'll be nice to clarify. One Nord Anglia student is wondering, what's the difference between plasma and fusion?
So plasma is the state of matter, and fusion is the reaction that takes place in a plasma. And it doesn't take place in all plasmas. Most plasmas aren't fusion plasmas. So most plasmas are, sort of cold and diffuse, especially if you look at space dust and things like that. There's no fusion happening there. There's no fusion happening in lightning. But if you go to a star or into one of these really extreme reactors, then you do get fusion reactions. Fusion reactions aren't rare in the universe, but they definitely aren't the dominant reaction in all plasmas.
Got it. And another Nord Anglia student is wondering, you showed us the states of matter, a solid, liquid, gas, and plasma. And one of the students is wondering, is it possible that there's even more states of matter that we could use for energy?
So there are more states of matter than just those four, but whether or not they're useful for energy generation, you'd have to get kind of creative. So one example of another state of matter is if you take a substance and you cool it down. So rather than heating it up to extreme temperatures, you're cooling it down to extreme temperatures. You start to get really strange quantum states of matter. So the example, if you're interested, the thing to look up would be the Bose-Einstein condensate. And basically, if you get atoms cold enough altogether, they enter the same quantum state and they act as basically a single quantum particle, but macroscopically. It's really incredible to see. But as far as energy generation, I think that plasma is probably the way to go because that's how the stars do it, and that they're the best energy producers in the universe.
And that makes sense. And now we have a question from a Nord Anglia student who's wondering, I think you mentioned magnets and magnetic fields really briefly. They want to know, is the Earth's magnetic field, does it work like the magnetic bottle that holds the plasma that you described?
So the Earth's magnetic field is generated because in the core of the Earth, we have all this molten metal. And that molten metal can also carry a current. And so you can use the same math that you use to describe plasmas to describe the core of the Earth. But the magnetic field of the Earth doesn't really hold any plasma in, it keeps plasma out. So the sun is constantly launching solar wind at us. It's just shooting out this kind of cold but fast-moving plasma. And when it hits the Earth's magnetic field, it basically pushes that plasma away from the surface of the Earth and towards the poles. And so if you have ever seen the northern lights or the southern lights, that's these high energy particles from the solar wind, this plasma, coming in and entering the Earth's atmosphere at the poles. So it's sort of the opposite process as in a tokamak. We're keeping the plasma out instead of keeping it in.
Well, I am really, really grateful that Earth's magnetic field is protecting us from all of that solar wind. That's really important for life. We're very special in our solar system to have that. Not all the planets do. So I am very grateful for that. We have a student on here on our call today who's really curious about some books, and they're wondering if they want to learn more about fusion, what are some books or things you might recommend they look into to learn more?
So to understand plasma physics, you really need a background in mathematics. And so if you're thinking about what should I study right now, really dig into your math courses, dig into your science courses. If you want something to work towards, you really maybe shooting for calculus and then differential equations. And then to actually understand the processes in the plasma, I think the textbook that I would recommend is maybe Plasma Physics and Fusion Energy by Jeff Friedberg. It's math heavy, but it has really great explanations for a lot of the processes going on.
Those are all really good recommendations. And I have a quick one as well. Before I got to meet Shon and learn all about the amazing work, I sometimes just look up plasma fusion on YouTube and watch a bunch of amazing videos that help explain the science in it more. So that might also be a really good starting place if you're a few years out from taking those advanced classes that Shon mentioned. But thank you so much for those recs. I think they're going to be really popular. We have a question from a Nord Anglia student who's wondering, what is the difference between the plasma you're talking about and the plasma that we have in our bodies?
Okay, so medical plasma is a totally separate thing. I don't know why they're named the same thing, probably because they have a common Greek root or something. But the plasma in your body is a component of your blood, and I think it has to do with your white blood cells, which help fight infections. I don't know a whole lot about it, but that's what I know.
Okay, so they're just separate things that have the same name. I think folks will find that happens in science a lot.
Way too often.
Yeah, that won't be the first time. We have a Nord Anglia student named Smayan, and Smayan's wondering, what do magnets have to do with plasma? Can you walk us through that again?
Yeah. So because a plasma is basically a bunch of ions and electrons, these are charged particles. Charged particles are affected by magnetic fields. And so if you have the right magnetic field configuration, you can basically keep these particles from walking away. You keep them in one spot, or in the case of a tokamak, you keep them in a donut shape. They're basically free to move along the direction of the magnetic field, but they can't go across it. And so if you have magnetic field lines that form closed loops, you're basically keeping particles confined to those closed loops.
Let's say we're talking about that donut shaped way of containing it and using these reactions to generate energy. Once you start, how long does this reaction last? And how long can the magnetic donut setup contain it?
So that's a good question. Current experiments, the plasma is sustained for only like tens of seconds. It's really, it costs a lot of energy to get going in these reactions because you have to heat up this plasma and you can't sustain that heating indefinitely. Once you reach the break-even point and the plasma starts to heat itself up through these fusion reactions, in principle, it could be sustained indefinitely. The magnets, the big breakthrough that's making spark possible is we've developed new magnet technology that basically, we have these superconducting materials that you don't need, once you put current in them, you don't need to keep supplying current. That current will just go around indefinitely. And so you can generate basically large permanent magnetic fields in this configuration. But right now, yeah, these reactions are pretty short-lived.
Got it. Okay. Well, I'm hopeful for the future. Now, speaking of sustaining these reactions, we have a student who's wondering how does this reaction sustain itself on the sun? Why does it work so well there and in stars?
It's a good thing to think about. The stars have a huge advantage over us here on Earth when we're trying to do fusion because they're huge. They're so massive that gravity is doing the job of confining the plasma. And so basically, there are magnetic fields in the sun, but they don't do the job of confining the plasma. It's mostly the mass squashing everything down and holding it there.
All right, so that's going to be pretty challenging for us to do because we would need objects bigger than our planet in order to generate that kind of pressure. Okay. So we have a lot of students tuning in from around the world today, which is so exciting. And they're wondering, we're talking about the research you're doing here at MIT, but can you tell us, are there other places around the world where folks are thinking about fusion, perhaps trying to build these reactors? Could you tell us a little bit about that? Definitely.
So there's the most obvious thing that comes to my mind is there's this huge international collaboration called ITER, ITER. I think it's International Thermonuclear Experimental Reactor. And basically, a bunch of nations have come together, they're pooling their resources, and they're building a massive tokamak to try to figure out how to get fusion to work in the near future. And so that's one big example. In the UK, there's a tokamak called the Joint European Torus. That's sort of a pan-European collaboration on the same topic. Korea has the reactor called K-Star. There's reactors in China. I think there's a bunch of reactors all over the world, but those are the biggest ones. And then there's smaller ones at universities across the world.
All right, that is good to know. So there's a few options right now around the world, and perhaps as research grows in this field, there'll be more and more places where people are researching this. So that could be really, really exciting. So the students on this call who are interested in pursuing that, just keep reading the news, keep following plasma news and fusion news, and you might find out that there's one in your neighborhood. Okay, so I want to take us back to you, Shon. We have a student who's wondering, what do you like to do for fun and why?
I would say my favorite thing to do for fun on like a day-to-day basis is to read. There's just so many interesting books out there about, all sorts of things. And so that's always really fun. I like to rock climb. I like to ski and canoe. Things that get me outside into nature and move me around. It's good to stay, active and to interact with the natural world. Canoeing especially is one of my favorite things to do because you're just floating along a river and taking it in. That sounds really, really fun and kind of peaceful at times too.
So we have another question from a Nord Anglia student along that same vein. What are some of your favorite books? Do you have any book recommendations, maybe in science fiction or not necessarily the textbooks like we talked earlier,
Yeah,
but reading for fun? Yeah.
a really interesting science fiction book series is called The Three Body Problem. It's about, so in the nearest galaxy to us, 4 light years away or so, there's a race of aliens who want to invade Earth, and we find out about them, hundreds of years before they're on their way. And it's sort of humanity's response to finding out that we're not alone in the universe and that there's hostile aliens out there. But then also it's this interesting problem of how can we, how do we as a species come together to solve a problem like that? Besides that book, I really also like fantasy books. The Wizard of Earthsea is a really fun series. It's just about a young wizard cruising around in a boat in this really just interesting magical world. Yeah, I could list a lot of books, but I don't know if that's really.
I think that's a really good start. I think I have to look up some of those titles myself after this. So now bringing us back to some futuristic aspects of this. We have a student who's wondering, when do you think fusion energy will become easily available for use in day-to-day life?
Okay. So the rough timeline kind of looks like this as far as I can see it. Spark will be done in 2026 or so, and hopefully it'll demonstrate net energy by the end of 2026, 2027. As soon as that happens, the company that's building Spark, Commonwealth Fusion Systems, has this plan to start developing and deploying commercial power plants as soon as they can. So give them 10 years to do that. Maybe by 2035, 2040, these reactors should be pretty common. And as the technology develops, as we figure out how to build these things more efficiently, the number of them will only increase. So probably give it 10 years and you'll start seeing these things.
Okay, that is really, really exciting. To follow that up, we have a student who's wondering, where do the materials come from that build these reactors and build the materials necessary for fusion?
So the biggest material sort of supply chain issue is for these superconducting magnets. They're built out of rare earth compounds, rare earth minerals, and barium and copper. So these rare earth minerals can be found all over the world, but they're sort of rare. And so that is a big issue that we need to address if we want to make a bunch of fusion reactors a reality. Something that I like to think about is that these rare earth minerals, they're only rare on Earth. If you go to space, you can find large quantities of them in the asteroid belt or, on meteors and things. So if we can get to space, then we solve a lot of our supply issues pretty quickly. Until then, we need to work on refining our mining technology so that we're not devastating the environment to build these reactors to save the environment.
Yeah, no, that's super fair. Now, I'm going to read a question off from a Nord Anglia student named Nias. And Nias is asking, if we're creating plasma by touching a door with that, static shock, why can't we collect the small plasma shocks to create a bigger jar of plasma? Could we do that to maybe avoid making a machine in the first place or without making a reactor?
It's an interesting idea. But I think that the problem is that these doorknob plasmas are so brief, they're so short-lived, that it'd be really difficult to, one, collect them, and two, to harness them usefully. Because it's like trying to bottle lightning. You can't really catch it. It just happens really quickly and then it's done.
And speaking of lightning, we have a question about lightning from a Nord Anglia student who's wondering, you explained to us that Earth's magnetic field helps protect us from solar wind. Why do we still have lightning then?
Okay, so the answer to this question has to do with the fact that the solar wind isn't the source of lightning. Lightning is generated because inside these big storm clouds, basically the wind will pick up a static charge by carrying dust particles away from the surface of the Earth and then carry them up into clouds. And so these clouds become electrically charged. They get a big voltage on them. And basically, once that voltage hits a critical point, it'll discharge a lightning bolt to equilibrate the charge difference between it and the Earth. And so that's why we have lightning, and that's the basic mechanism behind lightning. There's a lot of questions about how lightning actually works, but that's sort of the outline.
Got it. Yeah, lightning is super, super cool. Speaking of lightning in that example of plasma, we have a student who's wondering, and I think they saw the picture of that neon sign that you were showing in your early slides. What colors can plasma be?
A great question. Plasmas, the color of a plasma is determined by the gas that's in it. And so different gases will emit different light when they become a plasma. Air, so mostly nitrogen, sort of glows this pinkish purplish. Hydrogen glows red. Neon is green. I think argon is purple. There's a lot of different colors you can get, and different combinations of gases. You can combine the colors like paint. So, yeah.
That is really, really fun. Now we have a North Anglia student who's wondering, so let's say you have your reactor, you have plasma, you have fusion happening. How do you actually turn that into electricity that we can use?
That's a great question also. So the main product of fusion are these helium atoms and then these neutrons. And so these neutrons actually end up carrying out a significant fraction of the energy that's produced per reaction. And so the leading concept for generating electricity from these reactions is to basically surround your tokamak with some material that's really good at absorbing these fast neutrons. And as they absorb these neutrons, it'll heat up, and then you can then pump that, whatever that is, that's probably a molten salt, because those are good at absorbing neutrons. They're a fluid, so you can flow them. So that liquid salt is heating up. You flow it down, you exchange that heat with water, you basically boil water to turn a turbine and generate electricity. So it's a very advanced way of boiling water at the end of the day.
Okay, got it. And now we have a student who's wondering if you could describe your experiments and the work that you're doing. Walk us through what's happening in person. So you said there's a big team of folks working on this at the same time. When this is happening, you're standing behind, I think you said like multiple feet of concrete. What are you actually doing in that moment? What's going on?
So a lot of my work right now is testing different detector options to figure out what'll be the best choice to put on the actual reactor. And so we have ways of producing very small amounts of fusion in the lab. Basically, if you accelerate the fuel of the fusion and slam it into a target, you can produce fusion reactions. And so a large fraction of my work is basically going into the lab, setting up my detector next to this little fusion source, and then running away and closing the concrete door and turning on the fusion reaction.
Wow. Okay. I like the image of you, pressing that on button and then like just skedaddling out of there. I do that sometimes with my instruments too in the lab. So I totally understand. So now I wonder if we can begin to tie all of this amazing information you've shared with us today together. So could you tell us how fusion energy could be sustainable for us and why that sustainability is really important going forward?
So I think the biggest reason why fusion energy is sustainable is because the fuel is basically limitless. We're never going to run out of seawater, never going to run out of the hydrogen in space. And so from a fuel perspective, it's totally sustainable. And it's important that we find a sustainable source of energy because we're running out of fossil fuels. And things like solar and wind and hydro, they're important, but they can't fully meet our growing energy needs. So as a society, we really need to find an energy source that, one, isn't going to run out, two, isn't producing a lot of pollution and nasty byproducts, and three, produces enough energy to actually sustain human civilization.
And I mean, Shon, there's so many questions still in this chat that I wish I could ask today, but I'm going to leave you with one that I think a lot of students are thinking about. And they're wondering, maybe they want to work in fusion in the future. Maybe they want to help build detectors just like you. Could you tell them, what advice that you have for them? What are some skills they might be able to start cultivating to get to that?
I think that the biggest skills to cultivate are like a thirst for knowledge, so your curiosity, and the hard mathematical skills. I know a lot of people get sort of nervous when people say like, oh, you need to learn some math, but the mathematics that describe these reactions is really beautiful. And if you haven't seen beautiful math yet, you will see it soon. And once you see like how just like it describes reality on a level that's hard to articulate besides mathematically. And once you start seeing these relationships, it's hard to not look for them everywhere you look.
That is a really nice sentiment to send us off. Now, I want to tell the students before we go that if they're interested in watching some parts of Shon's abstract again, I know I want to watch the whole thing again as well, because it's just so cool. And I love the questions that student asked this time. Or they want to catch some of our past abstracts, they can find them posted on Global Campus or on YouTube. And I also want to give a quick shout out to our coming MIT abstracts. We have some really exciting talks coming up. One is on art and engineering and the whole idea of making at MIT. And then we have another coming on language and how we think, and do we think in words? I'm really excited for both of those. And now I'd like to thank the Nord Anglia Education MIT collaboration for making this series possible, for bringing Shon to your screens around the world. And I wanted to thank Shon once again for sharing some of his star power with us today. And I'm really, really excited to see what you do in the future. Thank you so, so much, Shon.
Yeah, of course. Thanks for having me.
Of course, our pleasure. Well, we'll see everyone next time. Have a good rest of your days. Goodbye.